Okay, so we are in the final stretch. The last 2 weeks, the plan is that, as I previously advertised in Physics 442 section, today we'll finish the harmonic oscillator. We will cover also approximation tricks, a little bit of a taste of higher dimensional quantum mechanics and many-body sort of rudiments in the next couple of weeks. There will be probably altogether 4 lectures. At least half of them will be just recorded and you guys will have to watch. And there will be one more homework plus the final exam, which will be take home. On the quantum computing side, we will talk about the Grover algorithm and error correction in the next 2 weeks, starting probably with tomorrow's lecture. Again, all of these will be recorded. And there's on the YouTube channel, I realized that I didn't post the Friday lecture until this morning, so that's already there. So the homework will be partly based on the Friday lecture. So all of you who missed it will need to go back and watch it. But there are also slides. I think the lecture took longer than I expected, almost 2 hours. So I think having slides is helpful. Okay. Again, there's probably at least 3 of you who, any questions, by the way, before I get started? Since you all have your video off, I assume that you're awake. I can only assume that you're awake. I don't know. But let's get started. Okay, so, the harmonic oscillator is sort of an oddball example where it's important, mathematically beautiful, a good pedagogical exercise. It's just everything at once. It's hard to imagine something that's more useful than the harmonic oscillator, both classically and quantum mechanically. So, of course, the way we think of it, and I think to a large degree, I'm following the chapter in McIntyre's book, those of you who have it. If not, I can send the chapter. I can probably do that if you want. Put a note in the chat and I'll send a PDF of this chapter 9. So the question is, right, so the basic idea is that we're interested in motion generally, but we're also interested in simplifying things. And one of the simplifications we consider is motion near an equilibrium. And so we imagine that there's a Hamiltonian or energy, which is momentum squared plus some potential. And the point of equilibrium is the point where you sit near a minimum of this potential, which implies that the derivative of the potential is equal to 0. So why is that the case? This is not a difficult question. Just to see that your fingers are still working, can you please type that in the chat? Okay, I'll wait for that. I'll ask that question again. And, those of you who don't type it in the chat, I will call on you just to see if you're awake. Assuming that that you're sitting at a point where the derivative of the potential is 0, you have to expand the potential at the second order in derivatives. Okay, we've got one answer. What was the question? Okay, all right. The question is, why is being at equilibrium is equivalent physically and mathematically to finding a point where the potential, where the derivative of the potential vanishes? Why is equilibrium equal V prime is equal to 0? These are equivalent statements, right? So if you, just to broaden it out a bit further, if you're sitting near the unstable equilibrium, I did not say stable equilibrium, but near the unstable equilibrium, the same is also true. The derivative is 0. Okay, so equilibria are generally points where V prime is 0. Anyway, please answer the question. But I'm going to move on. If we now look at the problem to the to the next order, which is, if V prime is 0, we're going to look at x squared. And at this point in the sort of a fashion characteristic of much of physics, we're going to try to solve this problem thoroughly by, but that of course involves making an approximation. The approximation is going to throw away higher orders in the potential, because it turns out including higher orders in the potential renders the problem really complicated. And so here the idea is that this is sort of a quintessential sort of a approach to physics problems rather than solving motion generally. And if, had you been a biologist or chemist, you would not say, oh, no, I just want to isolate something, idealize something. You try to solve an organism or something practical. As a physicist, you look for things that you can solve, and then you build your understanding of the universe around these ideas. And so here, by truncating the potential to just the quadratic term, it turns out we can solve it completely. Again, since most of you have seen bits of this story, and this is sort of a nice story to tell, so your physics 240 would instructor would have presumably spent appreciable amount of time on this. We think of this problem in terms of frequency scales. There's a frequency, which is the classical notion of square root of k over m. There is an energy scale, which you get if you know about quantum mechanics, which is h bar times this frequency is an energy scale. And so you can start rewriting the Hamiltonian using these scales. And lastly, there is a length scale, which its usefulness at this point is not apparent. It's just an observation that dimensionally you have h bar omega, which is an energy. So the Hamiltonian has units of energy. So h bar omega is an energy. There's an x squared. So there's a remaining coefficient has units of 1 over length squared. So there's a notion of length, which is the square root of h bar over m omega. And as usual, everything that has h bar in it, we think of it as something that's not classical, in the sense that these scales all go to 0 as h bar goes to 0. But we'll only appreciate the significance of this L much later. So it's hyperactive on text. Okay. There's an important aside here. Why is it called the harmonic oscillator? Okay, that's question 2. Can you type in the chat? Why do you think it's called harmonic? By the way, I find these chats to be very distracting to my lecturing, but if it helps engage, I will do it. That's an interesting question. You should think about what harmony means to you. It's not like a pipe with money, harmony. Right? It's harmony. Harmony means usually that there are more than one tones that can harmonize together. And those of you who've had any exposure to music or music theory, things that harmonize tend to be harmonics of each other. They tend to be these are sort of tones whose frequencies are multiples of each other, or at least the same. And so what you see is that the reason the harmonic oscillator is called harmonic is that if you think about its motion, the frequency of its motion does not depend on the amplitude. So if you take several instances of the harmonic oscillator, one of them has more energy, less energy, all of those will have the same frequency. Whereas typically, if you go back to the motion here, it won't be difficult for you to convince yourself that if you look at the generic potential like this, the more you swing it, the larger or smaller the frequency will be. In particular, you know that the physical pendulum, which is sort of the swing, does not have this property that the frequency is independent of the amplitude. And particularly if you think of a swing going too far, the amplitude will, the frequency will go down. It'll be less. Anyway, the interesting thing is that the consequence of this harmonic property of this particular problem is that we are essentially guaranteed that the quantum spectrum will be equidistant. And this can be derived with no real quantum mechanics. This can be derived semi-classically, as people used to do quantum mechanics in the early 1900s. And again, this is we don't usually teach the semi-classical approach because it's a little bit archaic. The only place that you might see it is in Physics 240, because that's more sort of a historical progression. And I think it's kind of interesting to just keep it in mind. So I thought that I would take a quick detour into that memory lane. And the way you do semi-classical quantum, actually, quick question. Have you seen semi-classical quantization? Yeah, have you seen semi-classical quantization before? Yes or no question. So I'm describing it now. So semi-classical quantization is when you think of the motion of particle motion in phase space rather than real space. So in real space, Newton's laws, are equivalent to second order in time differential equations. They are, they look like this. It's x double dot equals to something. We know the solutions of this are sines and cosines. There's no mystery. But to think about quantum mechanics, it turns out it's better to think in phase space. So instead of dealing with second order in time differential equation, you're saying, no, I want to look at first order in time differential equation. And you do this by paying the price of reintroducing momentum into the problem. So X and P, it turns out they follow this simple two-dimensional differential system where X dot is equal to P, because X dot is the velocity. I've set mass to 1 just to simplify notation. So X dot is equal to P over M, or P. P dot, V dot is the acceleration, and so that's equal to the force. So what you see is that this is an equation of a closed contour in X and P space, which is an ellipse or a circle, deformed circle, essentially. And so the brilliant insight, I think, that is traced back to Bohr and Sommerfeld, is that if you think of these orbits, they trace out an area in phase space. And this area has the right units. So an area in phase space is an integral of dxp or pdx, or in this case, right? So if I think of an area under the curve, it's going to be twice the area. I should put a little circle here. I apologize. Okay. It's the area enclosed by this orbit. And it matches by unit-wise, it matches the commutator between X and P. And there was an idea that's coming essentially from optics, that maybe, unlike classical system where this is just a number, maybe we should quantize this number in units of the Planck constant. Or if you remove this 2 pi to the other side, it'll be h bar, right? And so this is how people used to do quantum mechanics before von Neumann, for instance, before the Schrödinger equation. This is sort of the first generation of quantum mechanics. And so the interesting thing here is that if you think of what an area is, it's proportional to the size of the orbit squared, right? It's an area, it's pi r squared. And so you see that the area is going to be proportional to the amplitude squared, but amplitude squared is actually the energy. And so you see that requiring that the area of this orbit is quantized, and there's an index, integer index n, which keeps track of it, essentially establishes this relationship between energy and n. And this basically sort of implies that if you think of the energy, so what this basically says that not all orbits are allowed, right? Whereas classically, you are allowed to have any amplitude of the oscillation. Quantum mechanically, only certain amplitudes are allowed in this view of quantum mechanics. Okay? And so this suggests that the energy of the harmonic oscillator with this funny quantization condition is actually going to, the allowed energies are going to be, scaling with n. The exact answer, as we'll find out, is indeed that it's h bar omega n, and there's a 1/2, extra 1/2, which is important and which is missed by the simplest version of that quantization. But now we're going to derive it from scratch, right? And the cool thing about the harmonic oscillator, and this is sort of the only example where this can be done completely and simply and beautifully at the level of undergraduate quantum mechanics, is that you can avoid differential equations entirely, okay? And this is the so-called algebraic method, and all of the other applications of algebraic method try to apply the steps that we're going to follow through, but if you try to apply it to a more complicated problem where the potential is not an x squared, you generally have to work much, much harder. And the steps, and they're very simple. The idea is very simple, right? Because the harmonic oscillator has this simple Hamiltonian, and as somebody said, indeed, that the reason why we don't have a linear terms is because that would be a force, right? And forces mean that your initial idea of where the equilibrium wasn't right. It was wrong, right? You can always shift in response to a force and find a new equilibrium. And the next sort of sort of topic that we're going to discuss after this, which will be response to perturbations, and you'll see that more there. But for now, the Hamiltonian is the sum of the squares. And the cool thing about squares is you can take square roots and get back to simpler things, right? So if you just had x squared, obviously you don't want to understand x squared in its own right. You want to understand x and then understand x squared coming from x. So similarly, the idea here is that when you have things adding in quadrature, you can take a square root, factorize them. And so this is the example for numbers. The only difference now here is that x and p are operators. You should be careful because the cross term will be, whereas the cross term IBA plus IAB is 0 for numbers, the cross term for matrices is not 0. Okay. Okay. Whoops. What's happening? All right. Am I still sharing, by the way?
Yes.
Yeah.
Okay, cool. Wow, you guys are good at answering questions. I should ask more questions. Okay. Anyway, just very quickly, there's a way to motivate these steps, but this is one of the examples where it's easier just to write down the answers and you can, connect the dots yourself. The answers are that, the analog of this decomposition, let's just follow our nose through it and fix it up. All right. So we have a Hamiltonian, which is x squared plus p squared. The factors that we're seeking, and we're going to call them A, an operator A, which is x hat plus IP hat, with factors of m omega to kind of sort of make things work out. And the conjugate of that, so you can see that the lesson that you learn here is that the plus and minus pattern that's required for the cross term to cancel, is similar. So if A and B are now operators, then the A plus minus IB are basically canonical conjugates of each other, right? And so what that means is that, whoops, there's something in the chat. Let me just make sure. No. Oh, right. You haven't seen semi-classical quantization. Well, now you have. Well, that's really odd, actually, because that should have been covered in 240. All right. Never mind. Right. So you can now look at A and A dagger, and you can see what they are. And here it's important that X is Hermitian. So when you take A dagger, X dagger is X. But there's an I, and that's the thing that flips the sign. Oops, my PowerPoint froze. That's not good. Let's see what else froze. Okay, Zoom is still okay. Okay. This is fine. You know what? I'm gonna skip full screen. That seems to cause problems. Okay, so now we're gonna reconstitute this just to see what mistakes we've made. All right, so AA dagger, if you just multiply it out, if you multiply these two guys out, you'll get the x squared term and the p squared term with these coefficients. And then you'll get a cross term, which had x and p been numbers, this would have been 0. But because they're matrices or operators, this is not 0, but it's actually a simple operator. It's the identity. So x commutated with p is h bar. And so, sorry, it's IH bar, and I squared is -1. Okay. So bottom line now is that A dagger A is this guy, which is the Hamiltonian, x squared plus p squared. And you can check that, you know, these m omegas, you know, reconstitute into the Hamiltonian. And so that means that the extra -1, let's see, I should actually go through the factors of 2 carefully. So you can see that if you pull out this -h bar and you look at the 1/2h bar here, that will be -1/2. If you move out this m omega, there'll be 1/omega squared. So there's actually an exact match to this guy as advertised. If you just stare at this and then look at the form that we got with A dagger A, you can convince yourself that the Hamiltonian can be rewritten as h bar omega A dagger A plus 1/2. Presumably everybody has seen this at some point, hopefully. Okay, so that's, so far it's not clear what the purpose of all of this gymnastics is. And here comes probably the most profound thing here in all of this lecture. And the most profound thing is that the commutator of A dagger is 1. Right? You can go back and ask, well, how did this happen all of a sudden? Well, the commutator of x and p is IH bar. Well, look what we've done here in setting up these A's and A daggers. We've set them up to be dimensionless. Right? So at the end of the day, you know, a huge fraction of physics comes down to choosing your dimensions correctly and just understanding the structure that you're trying to create. And the structure we wanted to create was we wanted to take objects, which are x and p, which are physical observables with length and momentum and other things, and we wanted to create a counter. A counter is a dimensionless object. And so you can see that, you know, the A's and A daggers that are defined here, they're defined so that x is stripped of its dimension. So x is multiplied by something that has units of 1/L, 1/length. And this obviously is dimensionally matched. So by dimensional analysis, we could have already anticipated that A is dimensionless, A dagger A is dimensionless. And so it's a counter. It basically counts something, which is what we're working up to. But more importantly, the commutator of A's and A dagger is not H bar, which has dimensions, but it's just 1. So it's just a nice sort of a device, if you like, to, you know, count things. Now, what does it count, right? So let's find out what it counts. And this is sort of really the punchline of this slide. That if you think of an operator A dagger A and you commute it with A, you can check by just doing the commutators, which I've done for you here, that A dagger A commuted with A is -A. And similarly, if you take a dagger of this equation, you can convince yourself that A dagger A commuted with A dagger is a plus A dagger. Here's the math, okay? And since you probably haven't thought of it, recently or ever. This commutation relation implies that A dagger A is a counter. Okay. And the way to see it, at least the way we usually talk about it in physics, certainly McIntyre talks about it, is to say that suppose you have an eigenstate which is represented by some integer n. Right, and it's an eigenstate because when we hit it with the Hamiltonian, which is just A dagger A times h bar omega, you would get back e to the n. And the question is that what about the state that we get if we just hit n with, say, A? So now we just turn on the crank and say, okay, the only other operator we know of is h. So let's try to apply h to the state that you get if you hit A with n. Okay, well, we certainly don't know what this is, but we know what the commutator of h with A is. Let's use what we know. The commutator of h with A is HA minus AH. So that means that we can replace HA with AH plus the commutator. But the commutator of h with A was minus A. So that tells you that no matter what the state n is, HA is equal to AH minus h bar omega A. Okay. So this just follows from the commutator. Now, the cool thing is that we can now just do this calculation. We can say that h operating on n is En. En is a number, so it commutes with A. We take it on the other side. And this one is h bar omega A. So you can see in this one line that we've demonstrated, using just the property of the commutator and the fact that n is assumed to be an eigenstate of h, we've demonstrated that A times n is another eigenstate of h, possibly of different magnitude, possibly not normalized correctly. In fact, in reality, not normalized correctly. We'll tackle it next, but it's proportional to an eigenstate whose eigenvalue is different. So it's a different eigenstate. So this is why it's called, that's why A is called a lowering operator, because it takes you down the ladder of eigenstates. So you can see that A times eigenvector n is along the eigenvector n minus 1 in this filtered space. Okay. So it's called a lowering operator. You go through the same math, you convince yourself that A dagger n takes you up a state. So it's a raising operator. Now, just a small but extremely important detour. How big is this ladder, right? If we go back to here, right, the physical common sense tells us that, there's a ground state. The energy cannot be lower than a certain amount. The funny thing about this ladder, and this shows up in some exotic physics problems, not these kind of sort of garden variety physics problems, you generally expect that you should be able to reach the ground state of the problem, and there's nothing below the ground state. Now, how would that show up in this raising-lowering mechanics? And the way, whoops, I overshot the ground state, right? So here's the ladder, right? So A applying to 2 gives you something along the first the first excited state. A applying to 1 gives you 0. Great, that's the ground state. And the only way we know how to terminate the ladder is when A applies to the ground state, it annihilates it, kills it completely. You get a 0. Because after this, there's nothing left. The null vector is kind of a very singular, almost abstract notion. It doesn't exist. It's not in a vacuum, right? And the idea is that if you think of the energies as you march down this ladder, the energy is going down, 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 down. And the ground state has an energy 0 plus 1/2, right? Because a dagger, right? So think of what this 2, 1, and 0 is. It's a dagger A operating on, whoops, I made a mistake. Apologies. That should be 0. And so what you see here is what was advertised before is that this whole ladder is essentially h bar omega, and there's an n here which starts with 0 and goes up to infinity plus 1/2, and these are the energies. So far so good. We've computed the eigenvalues, the eigenvectors. If we're not interested in what bases they are, the only thing we're missing now is their normalization, and that's pretty easy to fix. We're basically asking what is the norm, assuming n is normalized. What is the norm of how do you normalize a times n so it's an eigenvector? It's a normalized eigenvector. Well, we just have to compute the norm. So you can see that the norm of a is n a dagger a n. And because we know that a dagger a is n itself, we're just counting the states. That basically tells you that the an gives you n minus 1 with the boost of square root of n, right? Because the norm is n, so you just have to take a square root to normalize it. Another way to state the same is that if you do work with normalized eigenstates, the matrix element of the operator A between n minus 1 and n is square root of n. And all the other matrix elements are 0, by the way. Okay. So you can do the same thing. You can ask, what about a dagger n? We know that that takes you to n plus 1. And so a dagger, you can use the commutator here and you will find that it's n plus 1. Okay. So that tells you that a dagger n, not surprisingly, is n plus 1 square root n plus 1. So all of this information, it's a matter of taste on some level, but it's worth having different perspectives. So you can think of the harmonic oscillator, because it's an infinite spectrum, you can think of it, but it's discrete spectrum, so you can think of it as infinite matrices. And usually what people do is they start constructing them from the ground state up. So the Hamiltonian is h bar n plus 1/2. So the ground state has its whole diagonal in the energy basis. So it's h bar omega over 2, 3/2 h bar omega, and so on and so forth. The A and A dagger operators, which we just computed, they're funny. They're not Hermitian. In fact, the only non-zero elements are this one away from the diagonal element. And here the values are square root 1 and so on and so forth. The conjugate of that, of course, is a dagger. You see that they're real in energy basis. They're real because they're just, they're advancing you up a state or down a state. But the important thing is that because of they're not natively normalized, they're these square roots that are dangling. Okay. So a much more interesting example, which you can reconstruct from all of this, are the matrix elements of X and P. If you go back to the definitions, that's what the matrix elements are. And you can see that X and P have the same kind of structure as A and A dagger, except multiplied by these dimensionful factors. And because they're Hermitian, they're actually symmetric under conjugate transpose. So X is real, P is pure imaginary, but they're both Hermitian. All right. I think we're basically done with the first half of the lecture. I just want to make sure that people, just how lost are we? So let me, maybe I should have created a poll so we could do this easier. Are you lost? Any questions? Okay. I'm not sure why it's better to use chat rather than sort of unmute, but I would like you to kind of indicate. All right, let me barrel through the rest of this because this is sort of very standard stuff. Well, this actually relates to problem 3 on the homework 6, which some of you are still working on. So let me just go through this for that reason, if nothing else. So you should notice how there are no, these matrices are primarily are mostly empty. Okay, that means that if you take a generic state, right? Well, the upshot of what I'm going to tell you is that when you have when you have operators, most of whose matrix elements is 0, in physics jargon, this is called a selection rule. There's a reason why this operator does not connect certain states, right? Whatever the reason that might be, that's the selection rule. But once the selection rule is active, that means that certain natural frequencies are just missing. So let me work through this example here. The example that you had of the square well after the quench was more complicated in the sense that there was more interesting information to compute. Here, it's kind of like all by inspection. Once we've set up the stage, the basic idea is that suppose you have an initial state which is not an eigenstate. It's just a mixture. Just consider an arbitrary mixture of random just states. ANs are some numbers, right? And the question is that what is the dynamics of an observable, say X in this state, right? So here's the complete formula. Because you're sandwiching psi from left and right, what used to be a single sum on n is now a double sum. And so because n is a dummy index, I'm going to use m and n. And so am star an, basically am star comes from the conjugate. Here's an expectation value. Now I'm sandwiching this. And the crucial thing where all of the dynamics comes from are these exponentials. And you can see that the energies come in pairs with plus and minus because of, again, complex conjugation. And so the frequencies that show up in the behavior of X, we can call them omega sub m. Oh God, omega sub mn. Okay. And that comes from differences in the energies. So you can see already that energy itself is less important than the difference in energy when it comes to physical observables. Okay. And because what we know about the structure of X, that it only connects adjacent eigenstates, you realize that it really doesn't matter what state you start with. The only frequency you'll ever see, right? Because you have this spectrum and you can in principle have states whose energy difference is enormous, right? Because it's all going up states up the wazoo. But the only frequency you'll ever observe when you observe X is this frequency omega, which is the fundamental frequency of the problem. Okay, so it's only plus minus. Now, what about other frequencies? How do you observe them? Well, a clue comes when you basically have to construct operators that connect states that are not adjacent. And because you know the structure A and A dagger, you know that A squared is such an operator. It connects states. It's basically raising twice, right? It looks like this. It's zeros on the diagonal, 0 first row near the diagonal, and the second one has matrix elements, which you can compute. It's a double square root of a product. And that basically means that, if you try now to go to things made up of A squares and A daggers, for example, X squared, you can write it out. It has a contribution which is A squared and A dagger squared, but also it has a contribution which is containing A dagger A plus A dagger, not minus. If it was a minus, it would be called a commutator. A plus is called an anti-commutator. And anti-commutators are, in some sense, they're non-quantum because they exist there even in, if you replace these with numbers. And in particular, this anti-commutator turns out to be, you can convince yourself, 2n dagger, 2n, the counter plus 1. In other words, it's proportional to the Hamiltonian. So the funny thing is that when you look at the time dynamics of this psi, of this x squared, you're guaranteed to get a contribution which now oscillates at twice omega, but you're also guaranteed to get a contribution proportional to the average energy, which doesn't oscillate at all. I put dots here because I didn't want to work out the constants, but so the funny thing is that, and you shouldn't be surprised by this, that the energy is x squared plus p squared. But if you only look at x squared by itself or p squared by itself, they have, these rapid oscillations cosine to omega. But on average, x squared actually is given by the expectation value of the energy itself. Okay. This is related to something called the virial theorem. I think depending on who taught you physics 120, you would have seen that. I think that's in the textbook, in the calculus-based physics 120. All right, almost there. So this basically concludes sort of the discussion of, at this point, you know everything about this problem that you would want to know. Potentials that are not part of this problem. So had you only been interested in this problem in its own right, my internet connection is unstable. I hope this is still okay. Okay, all right. So the next thing we're gonna do is we're gonna look at what these states look like in real space, right? So so far this has been much more abstract than all of the other examples that we've done of the infinite square well and all that scattering stuff. Now we want to work things out related essentially to real space, okay? And again, here once again, things can be done very elegantly, right? And let me remind you, and you'll be reminded of this much more when we go to 3 dimensions, sort of next week, that the ugly part of quantum mechanics is having to solve differential equations. Right? Because differential equations, they're a mainstay of 19th century physics. There are tricks to do them. If you know the tricks, you might find them beautiful, but it's a technical layer of the theory which is sort of, so without further ado, the cool thing about the harmonic oscillator is that you can simplify the differential equations part. So far we haven't used differential equations at all, right? We've used these algebraic manipulations, doing commutators. So it turns out to work out wave functions, you have to bite the bullet and solve some differential equations, but you can be super clever about it. The not clever part of this is described in old books, and that's how you get, maybe I'll send that as a homework problem. But the clever part is to think about the equation, not the Schrodinger equation, but the equation for the ground state as a differential equation. The equation for the ground state, this is the one that I underlined here, is annihilation operator operating on the ground state wave function giving you 0. Okay. So let's write that out as a differential equation. And here I'm going to come back and fully utilize this length scale, quantum length scale that I defined earlier. So instead of carrying around all these factors of m omega h bar and all that junk, I'm going to say that the annihilation operator, which we need, or the lowering operator, or it's also called annihilation operator because it annihilates energy, removes energy from the system, can be rewritten, and this is kind of like super beautiful, I think. You take all of this junk and by introducing a length, essentially doing dimensional analysis, you can rewrite all of that as 1 over root 2 x over L plus L d by dx. Okay, so we've replaced x and p with their real space representation, which is x and d by dx. right, with h bar over I. And just a little bit of tying up loose ends, we get just purely dimensionless kind of an expression. And now we're ready to go, right? Because if we take this A and then you form a differential equation out of this equation, what you're saying is that the ground state wave function obeys this differential equation. It's x over L phi naught of x plus L phi naught prime of x is equal to 0. Okay. And we can solve it. We can solve it without guessing. Okay. We can solve it by brute force integration or whatever, direct integration. Massage, massage, massage. Bring all of the terms with phi naught to the left hand. You get phi naught prime over phi naught is equal to E minus x over L squared. With a loving eye, you'll see that this is an expression for a derivative of a logarithm. And when you take a derivative of the logarithm, you'll get phi naught prime over phi naught. So that means that you can now integrate this up to a constant. Sorry, something I dropped. In principle, here there could be constants, but you can convince yourself that those constants are either normalization related or forbidden. Okay. So the integral of the logarithm is e to the minus x squared over 2L squared. That means that phi naught itself is the beloved Gaussian, right, that you've already seen on the homework. So you know how to normalize the subject. Now, you can plow through the rest of it, but before we do that, let's simplify. I already said that this is already achingly beautiful, that you've gotten rid of all the physics and it's all just length scales. You can do better. You can replace x over L with a dimensionless variable psi, and write the ground state wave function as e to the minus xi squared over x, keeping in mind that xi is x over L. Now, the cool thing is that now you can go to town. You can write down what phi 1 is, the first excited state, by taking a dagger and applying it to phi naught. Remember, a is psi plus d by dx psi. A dagger is the same with a minus sign. So you can see that by applying these, so at this point, we're not solving differential equations. We're just applying algebraic sort of steps. We're taking derivatives also. So you can see that c minus d by dx c of the Gaussian is just c with an extra factor of 2. These two guys add up. The second wave function can be obtained by applying a dagger to the first one. You can see that it's going to be 2c squared minus 1 and so on and so forth. And the cool thing you observe when you play this game is that, well, okay, this is what the wave functions look like. Since I have the next slide, I'll save the insight until then. So this is the Gaussian. This is c times e to the minus c squared. The red one is a Gaussian with an extra prefactor of c. 2c squared minus 1 is a second order polynomial. Right, and the basic thing that to note, and this was also true of the square world problem that we solved, is that in these simple standard quantum mechanics problems, in fact, most problems involving quantum mechanics, the ground state is the tightest, the nodeless. It doesn't have any zeros, and the basic idea is that whenever you raise the energy, the wave function starts wiggling more. Basically because it has more kinetic energy, so it has to have more oscillations. And oscillations generally mean that it'll cross zero several times. And zeros are called nodes. This, again, all this terminology was lifted from wave mechanics. So if you have a wave, a node is where the wave goes through a zero, where there's no intensity. And so the funny thing is that these wave functions, as they gain in energy, they have these places where the probability of having a particle vanishes. These are called nodes. Okay, so there are a couple of other items. One of them is to work out the momentum space picture, which is actually kind of silly because, x and P are sort of related to each other by derivative, going both ways. So you can check that, for example, that in the same way that we wrote P as H bar over I d by dx, you can write X as IH bar d by dp. And if that's the case, then you can close your eyes and go through all these steps and arrive at an expression for the lowering operator that's not written in terms of X and d by dx, but rather P and d by dp. And so you can see that you can define the ground state wave function not in real space, but in momentum space. Now, the cool thing is, again, I'm mentioning this because you guys, at least those of you who have done homework 6, are experts on Fourier transforms and other stuff dealing with Gaussians. You can verify that we've derived the same wave function in different representations. Here's a representation in P space, and here's a representation in X space, real space. But it's the same thing, and they're related by a Fourier transform. Okay. And this sort of thing should be expected because your Hamiltonian is essentially symmetric under exchange of X and P up to rescaling. Okay, I think the last thing that I have to say for now is that the generalization to higher dimensions is very easy. It's trivial, in the sense that what we've done with X and P can be just replicated to have X and P sub X and Y P sub Y with independent simple commutators, and P sub X will be related to d by dx, and P sub Y will be related to d by dy. Then the Hamiltonian would be written as sum of P's and sum of X's squared, obviously, and so on and so forth. You can rewrite it as sum of A dagger A's, but now each polarization, as it's called, X and Y, will have its own set of creation annihilation operators. The wave functions can be written like this, and so on and so forth. So the ground state is what it is here, but now you can see that the excited state can be 0, 1 or 1, 0, and they have the same energy. So what you see is that the number of excited states, whereas previously you used to have just one excited state, in 2 dimensions, you'll have your first state, it will be doubly degenerate. Your second state, because it's all linear, you can have this 1, 1. So your second state will be triply degenerate. And one can observe how this sort of proliferates. Basically, the higher in energy they go, the more the degeneracy is. And one way to think about this is that the ground state is a dot, just smeared. The first excited state is, a small circle, and you can fit 2, orbitals that are orthogonal on it. The second excited state, this analogy is not perfect, but when you go out to large excited states, at that energy, you can draw the classical orbit, and you can see that the size of this orbit is proportional to the energy, and so it's proportional to n. So you can loosely think of the degeneracy as being essentially tracking the energy of because the circumference, if you think of the degeneracy as roughly the circumference of the allowed energy surface. Again, this is going back to semi-classical quantization. Okay. All right. I think this is all I had to say. So this is basically all of chapter 9 in McIntyre, and it's a nice self-contained sort of topic that has applications, everywhere. Any questions? So are there people still struggling with homework 6? Those of you who are 442 people. I'm concerned about that because I know 1 or 2 of you turned it in. I think one person reached out to me and we had an hour-long office hour. He is not on this chat. He said he'd turn it in. I don't know if he did. I think there's at least 1 or 2 people on this lecture right now who haven't turned it in. I haven't checked the thing. So if you want to ask me questions about homework 6, now is a good time. Or questions about the lecture, obviously. Any signs of life? Okay. All right. Hope to see you tomorrow or Wednesday or both. Any other questions before I sign off?